An electron moving with a speed of 5 times 10 to the 6th meters per second enters an E field having a magnitude of 10 to the third newtons per coulomb. The direction of the E field is in the direction of the electron's velocity. Part A. How far will the electron travel before coming to rest? Part B. How much time will elapse between the time it enters the E field and when it comes to rest? Part C. If the E field ends abruptly after 0.8 centimeters, what percent of its initial kinetic energy will the electron lose as it passes through the field? Alright, so we're given that the velocity is equal to 5 times 10 to the 6 meters per second, and that the E field is equal to 10 to the third newtons per coulomb. So I just defined that, to the right is positive and up is positive as well. So we need to keep in mind the things that we learned, that the E field corresponds to a positive test charge. So the electric force, if there was a positive test charge here, would be going this way, in the direction of the electric field. However, since this is an electron, the electric field actually exerts a force in the negative direction. Now that sounds counterintuitive, but think of it like this. A positively charged item can't possibly have a force in the same direction as a negatively charged item or molecule, whatever this thing, particle. It can't have a force in the same direction if that force is exactly the same in magnitude and direction, because negative charges attract, positive forces go outwards, they repel. Okay, once we have that, this problem becomes a lot more straightforward. So the electric force is equal to Q times E. We have the value of Q as 1.6 times 10 to the negative 19 coulombs, and we have E, which is 10 to the third newtons per coulomb. Again, this is not, we can say that it's negative, but I prefer not to, simply because I know that from what we learned that the force is going to be in this direction. So I just keep the magnitude of the force, which is 1.6 times 10 to the negative 16 newtons. So the sum of the forces is then equal to ma, and we can figure out the acceleration and find out after that the displacement that the particle moves through kinematics. So we have the force 1.6 times 10 to the negative 16 newtons, and that's equivalent to the mass of an electron, 9.11 times 10 to the negative 31 kilograms, and then multiplied by acceleration. Acceleration is approximately 1.76 times 10 to the 14 meters per second squared. That's really big. Again, it's going this way. It's going this way. The same direction as the force. So the final velocity we have as 5 times 10 to the 6 meters per second. If we're solving this as in a kinematic method, the initial velocity is 0 meters per second. We don't know the time. We want to find change in x. And so we have three quantities here. And I just use velocity final squared is equal to velocity initial squared plus 2a times change in x. So this is 0. This cancels out. 5 times 10 to the 6 meters per second. Quantity squared equals 2 times 1.76 times 10 to the negative. I don't know why there's, excuse me, that's not supposed to be there. No negative. Whoops. It's just supposed to be like that. 2 times 1.76 times 10 to the 14 meters per second squared times change in x. We isolate and we get approximately 0.07 meters. Part B. We're asked how much time will elapse between the time it enters the E field and when it comes to rest. Again, we can use kinematics. This is quite fun because we're getting reminded of mechanics, touching up on that. So again, we are given these quantities and we can solve for time. Change in x equals velocity initial plus velocity final over 2 times time, and 0.07 meters equals 5 times 10 to the 6 meters per second divided by 2 times time. And time is approximately 2.8 times 10 to the negative 8 seconds, or 28 nanoseconds. So again, I just use another kinematic here, fairly straightforward. Okay, now the last question asks, if the E field ended abruptly after 0.8 centimeters, what percent of its initial kinetic energy would the electron lose? So here we're given that change in x is 0.008 meters. Acceleration is the same value. Velocity initial is 0 meters per second, but we don't know velocity final and time. So velocity, or excuse me, I just used another kinematic. Velocity final squared equals velocity initial squared plus 2a times change in x. I just substitute my values for acceleration and change in x at the point 0.008 meters where the E field abruptly ends. And velocity final is approximately 1.68 times 10 to the 6 meters per second. So we want to see how much kinetic energy was lost in this encounter. Now, this makes sense because there's a force going this way. The velocity of the electron is actually in the direction of the E field. But don't get confused because the electric force is actually going in the opposite direction. And if we know that, then it makes sense that it loses kinetic energy. So we can just use a little percent error deduction kind of thing. So initial kinetic energy minus final kinetic energy divided by initial kinetic energy should get us the percent error, kind of similar to that actual minus theoretical, that kind of thing in chemistry. So if we substitute using the kinetic energy formula, which is 1/2 mv squared, 1/2 times m times the initial velocity. Whoops, actually these should be switched around. Okay, imagine this goes here. Okay, so this should be 5 times 10 to the 6. I don't know why I wrote 1.68, but I calculated it. That's 5 times 10 to the 6. So 5 times 10 to the 6, and this should be 1.68 times 10 to the 6 meters per second. And that's all divided by the initial 1/2 times 9.11 times 10 to the negative 31 kilograms times 5 times 10 to the 6 meters per second squared. So we get a value of 0.88, around 0.88, or 0.89, whatever. And from that, just 1 minus that should give us 0.11, which is the amount of kinetic energy that we have lost, 11%. And this, just a little clarification, this represents the kinetic energy left over after the electron has passed through the E field.